That's great. Okay, started record. Okay, so what I'm saying is that, see here, this uh, yeah, input file is fine. That means I think the material properties and section, everything is okay. But there is some instability there. That's what I think. It might be just this one. So I'm trying to make.
Yeah, Dr. Neta, if it's going to be that one, then I mean it might also be that this one on the left. I mean on the left side.
Yeah. It could be that one too. But then if we have defined it as a beam, then it should be fine. So that's what, yeah, you're right. It could be either one. I mean, if it is this, then for sure this is also causing problem. Uh, let's just I already assigned this. And then beam. Yeah, that's all it should be. Then, yeah, two node linear beam in a plane. That's all we want. Element shape, okay. Why this doesn't work. Yeah, okay. So let's see. Okay, property. Okay, let me see. Ah, see, we put truss here. That's the issue. Okay, let's just make it beam now. We don't want truss. Okay, see, type we made truss. Let's make a new one. Beam, beam, not truss. Okay, that's why it was causing. Okay. Uh, this is material steel, blah, blah, blah. Everything is okay. Oh, okay. Circular. Okay, so now we should give a meter. So 0.5 millimeters. Okay, you got it, right?
Yeah.
0.5 millimeters. So 0.0005 is meter, right?
Yes. The unit we are working on is meter.
Okay, yes, but you need to keep in mind in abacus itself, there is no unit. So if we give in meter, we need to make sure we give everything in meter. We need to make sure we give everything consistently. The elastic modulus in Pascal and then loads in Newton, right? Did
Okay,
you
so
got what
yeah,
I'm saying?
that is SI unit.
Right. So if we are choosing SI unit, we need to make sure all our quantities are in SI units. The elastic moduli, loads, all the lengths are in meters. So if you change anything there, then it will all get thrown off. You got what I'm saying, right? In
Yes.
abacus itself, there is no unit, so it will not do any unit conversion for us. Okay.
Okay.
So okay. No steel beam section. No section.
Detonator, can we delete this
Okay.
steel
Okay.
truss section, or we can leave it there?
It's fine. We are not using it. Let it be,
Okay.
because actually this thing, if we don't have this one and this one, then it should be fine even with trust, and our result should not change that much. You see why? Because this thing is statically determinate, except for these ends are unstable. You can see, right? If you have hinge at this node and this node, if you have hinge, then it is unstable, right? It will just collapse, right?
Yeah.
That's why it could not do it. But uh, but uh, if you remove this and this, then there should not be any instability after that. You see what I'm saying?
Yes,
Even
I
even
see, but structurally, I think it still depends on the length. If the length is not too much, if the length of those, if they are not too much, I think it can. I mean, the joint here can still hold it. But if the length is just too much, it's going to be like a cantilever. So it might not be. It might be unstable.
no cantilever. Okay, okay. So you see, we don't need to worry about any kind of failure. See, we don't need to think of buckling or anything like that, because right now we are ignoring all that. We are just thinking everything is linear elastic and we are doing it. The only instabilities we need to worry about right now is joint constraints and restraints.
Okay.
Of course, in a real system, what you're saying, yes, absolutely, that is true. But this is a model, right? So we can give whatever we like here. Okay.
Okay.
Okay. So let's just assign. Okay. See, I said no to those sets because if not, it will unnecessarily create more and more sets. So do you see, every time you make a selection, it will ask you whether to create a set. Unless we specifically need some sets like corner or edge or something, it's better not to keep on creating some sets, okay?
Okay.
It will just unnecessarily add things. Okay, steel beam, we said okay. Okay, so everything is assigned section. Okay, so now let's see. Ah, okay, still instability. Okay. Where's the instability? Not sure if it is somewhere in between. Okay, okay. Let's see. We know input file is okay in this. somewhere is the joining problem, and I am not sure where. So let's just make this using try let it this one I saved. Okay, I
Yeah.
saved this one here. Yeah, I just put like this kind of models and just saved here. So let this be. Now let's just make this same thing using repeating method. Okay, just a moment. Span. So by the way, if you just wanted to take a look and just searching for pen, and if by the time you wanted to see, this is all fully, nothing is done. Everything is only proposing, except
No.
this figure 4 and 6 are done. Oh my God. Forgot to change the figure number. Okay, let me see. Just one moment. Let me see if it can just still let me do. Uh, oh, it's still there. Okay, let me check. Okay, it is here. Okay, shit, all are figure 4. Okay, let me just fix that one thing. It will only take a second. Sorry. One, two, three, four, five, six, seven, eight, nine. Okay. I don't know what will happen, but okay. Anyway, that was the poster. Uh, let me let me get time. what is the shape? Okay. Okay, if I do here, you cannot see. Let me do on this. Just one thing. Oh. Oh, I can't remove this now. Yes, yes, yes. Okay. Sorry, I'm just trying to set up the electronic pen. Kehinde.
Yeah.
Yeah, I'm saying I was just setting up the electronic pen
Yeah, okay.
because if I write on paper, you cannot see what I'm doing. Now, just a minute. Make sure of the length. Ah, sorry. Okay. So this was 1 centimeter.
Same thing, 1 centimeter.
No, I think all are 1 centimeter. Okay.
Yeah.
Okay. Let's make the same.
Okay.
So we need to make two now. Okay. This is what we need to make. Mhm. Okay. No. So first, if we make just this. Okay, let's do this. Excuse.
Oh, sorry.
Thank you.
You're welcome.
Okay, let's do this way. How many we put? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, 20 and 20, right?
Yeah.
5, 6, 7, 8, 9, 10, 11, 13, 14, 15, 16, 17, 18, and 20. Okay. Okay. So 20. So how many meters? Roughly we have 1 centimeter, no, 2 centimeter, 20 times. So 40 centimeter. So how many meters? 0, we can take 0.5. That should be enough. Okay. Now let's make only this. Let's make 0, 0. Then we go to 0.01, right?
Yeah.
Oh, I went horizontal. Okay. 0, 0. X is 0, y 0.0. Okay. Now next point should be, okay. So hexagon, what is the angle? 120. So yeah. 120. Hmm. So what I'm saying is, right?
Yes.
So this point should be how much? Okay. First day. Now, then this point is what?
Same thing.
Yes. Now, zero. Okay. Then this point is how much? How much is that? Okay. Okay. Now,
Yes. Well, Dr. Nathan,
yes.
I can see that we said earlier on that each side is 1 centimeter.
It is still. You can check right now. See. Okay.
Oh, it is, yeah.
Okay. Now we don't want this element. Uh, auto trim. Now we want to do repeat all these. Now so in X direction we want 20 times, right?
Yes.
And our spacing, it should be exactly this point. So 0.01 times √3. So our spacing one seven three two 0 5 0 8 0 8.
Dr. Nathan, before you do this, we have to put the diagonal in the middle.
We don't need to put right now. Let me tell you. We don't need to put right now. I will show you.
Okay.
Yeah. Okay, so we did this one. Now we want to repeat this upstairs 10 times. So now this to this is how much spacing? Let's check. We need to shift that much. So how much is this spacing? This one is 0.005, 0.01, 005. So here to here is 0.02, right?
Yes.
Then this is another 0.01. So 0.03 we need to shift everybody. Okay. So now pattern, everybody done. Then nothing. I know that. 10, 3. Say okay. Now we will make just one. Make just one from here to there. Okay. Now we will move this one. How many times? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 19 times. Okay. So pattern, sorry. Yes, pattern this. So direction 1, we want 19 times. Now direction 2, we don't want right now. What? Okay, that's okay. 19 times. And what is this distance? Distance is between these two is how much?
I think it's still 0.0, should be 0.02.
1 times root 3, right? This here to here. 0.01 times root 3, right?
Yes.
Okay. So okay, so it is correct. 0.0. Yes, that is correct. Okay, so we got those. Oh, I should have done 20. Okay, do again. Down, 20. Okay, so that's done. Now we take all of them up, right?
Yeah.
Okay, now select. Oops.
Dr. Nathan, but
Huh?
I can even get the dimension from the model itself.
Yes. Oh, okay. So I need to go do each one. Stupid. Okay. So pattern, this is not a good way. Okay. Anytime if you're doing a repetition in computer program by hand, it's not a good way.
It's not a what?
No, I'm saying anytime if you're doing repetition in computer program by hand or manually, is something wrong we are doing there. But okay, we have only 20, so let's do.
There's one here. Okay, yeah.
I missed.
Close that. This one here.
Yeah, I missed one.
Yeah.
Okay, now on. Okay, so what is that distance? 0.03, right?
Yes.
So, but how many times? 1, 2, 3, 4. No, one is just this. 1, 2, 3, 4, 5, 6. What happened to my mouse? Oh, you can hear me still?
You say what?
Oh, I'm okay. I thought my computer got stuck. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. Is it? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9 times we need to repeat. Entities to pattern. Done. Now direction 1 is nothing. You know that. Direction 2 is 9, 0.03. Okay, so now we got this part, right? Okay, so now so now uh, still one more thing before going to the rod. So let's do this. here to there. Now let's do pattern of this guy. Okay, done. Now 9 times and 0.03 should be okay. Okay, so I should have
one is missing.
Yeah, one was missing. Thank you. You got it. Okay. Okay. And okay, so that's good. Now let's put the rod. Let's put first there to there. Okay. Okay. I was not sure if I let's just zoom and do so that okay. See if that little box should appear. If not, we are not on that node. Okay.
Yeah.
Okay. So now we can pick again pattern. This one, how many we need? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We need 20 this way. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The vertical. Okay. So 20 in X and 10 in Y. Okay. So 10 in Y, 0.03 is correct. That's fine. But in X, what is the okay, it is still 2 square root of 3, right? Times
Yeah.
0.01. Okay. So that should be okay. Let's just say okay. Okay. So we got these now. Now let's do the other one. Okay, there. Now pattern with this. Okay. Now how many times in X? 1, 2, 3, no, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, 19 in X, in Y, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. This is 9, 19. Okay. 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 So now it is right.
Yeah.
Okay. Okay. We need to wait. We need to wait for a bit. So while we are waiting, oh, okay, already done. Okay. Okay. Just one moment. I need to go to restroom.
Okay.
Hello, you are there? Can you hear me?
Yeah, I'm here.
Okay. Okay. So why something looks different here? Uh,
Something look different. You see the same thing.
yeah. Okay. Now let's make the profile. Some end. Oh, oh, okay. Oh, okay, Doctor. Okay. But I guess you usually come every day.
Yeah, because this is the time to do research. I want to push this thing to move it a little bit.
Yeah, even for the if I at home it's very difficult to
Yeah, and I know. Yeah.
yeah, it's Dr. Chimba. He just left.
Yeah, I heard his voice.
Yeah, yeah, man. He is every day from I think minimum 12 hours he's here every day. I wish I could do, but after it's very difficult at home. When I was in postdoc, yeah, I could do, but is yeah, it's right now it becomes unfair if I do because we are only two. So with this COVID, it's
It's very difficult.
just crazy. It's really very crazy. Oh, just a second. Just want I think still my people cannot come to you. Yeah. I guess you should know also you're coming, right?
You know what?
I mean, I guess you also should have checked the news about the third wave now.
Yeah, the one from South Africa.
Yeah, I forgot the name of that variant, but
Omicron. Or
oh yeah, Omicron. Yeah, Omicron. Yeah. Okay. Uh, so we made circular. Oh, same thing. Number of zeros is correct. Yeah. Okay. So we made the section. Now make the section. Beam. See, it should work with truss too, but let's just do beam first, and
okay.
then we will do truss. Because you see, this is statically determinate, right? It's not a mechanism now, right?
Yeah.
Uh, okay. Since we did something different here, those end branches are not there now. Okay, anyway. Uh, let's make what to call it? Section. Beam. Yeah, profile steel section. Okay. Oh, we haven't made material. Let's make material. Okay, after this, I wanted to show you how to run the micromechanics thing, but not sure if we can get to that. I hope we can. Oh, were you able to search some other course where I mean, somewhere where they are just teaching the micromechanics?
No, I've not had, no.
Oh,
Did you want me to search some courses online? You didn't tell me that, Dr. Nathan.
okay. Okay. I thought I said, maybe I must have not.
No, you told me you will search for me and let me know.
Oh, I said I will search. Okay. Yeah, but I didn't. These last few days were just. Yeah.
So do you want me to search now?
Yeah. If you not right now. Right now we do this. After we finish this, then you can search.
Oh, okay.
Yeah. Yeah. And
Online? It has to be online.
yeah. How else can you do it? It has to be online.
Yes.
Or the only thing is, if here, then I can check if anybody is offering in Vanderbilt.
In where?
Vanderbilt, because you are coming here anyway, right?
Oh, you mean in Vanderbilt? Vanderbilt?
Yeah, that's just
Yeah.
10 minutes from here. You can, if they allow there, then you can take this.
Oh, okay, that's fine.
Okay, so Young's modulus is 200 GPA, but like I said, we have to give Pascal, right?
Yeah.
200. So G 1, 2, 3, 4, 5, 6, 7, 8, 9. Can you count? We have 11 zeros. 1,
1,
2,
2, 3.
oops. Okay. Oh, okay. 1, uh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Poissons give 0.35 and steel. So, okay. Now everything is okay, right?
Yeah.
Now make this section steel section. Okay. Now let's assign the section to our part. Yeah, see, that's what I was saying. When you do, don't put check mark on this create set, okay?
Yes.
Because it will unnecessarily create hundreds of sets, and
Yeah.
which we don't need. Okay, so now section assignment is done. Now let's put the boundary conditions. So, oh, we haven't created any assembly. Okay, so let's make the assembly instance. So just choose always dependent mesh on part.
Okay.
Independent is something a bit advanced. I don't know very well. Unless you know how to do it, don't choose it. Okay.
Okay.
Say okay. Okay, so we made one instance there. Now let's go to boundary conditions. So I told you, right? It is quarter symmetry. So did you understand that one?
Yes. I understand symmetry.
Oh, you know quarter symmetry. You're doing finite element from a while, right?
Is it what?
No, you're doing finite element from some time, right?
Yeah, I did final element back home, but you know,
Okay.
it wasn't advanced like the one we are doing. They are gonna be doing here.
Oh, this one is not even, I mean, we are just using software. We are not even doing any finite element here. Yeah. Oh, the next semester, you registered for finite element, right?
Yeah. Did you? I think you give it. No, I will check. Do I check? Because you are the one that sent me the.
Yeah, I
You know.
sent you. I sent you finite element. You asked me the courses, right?
Yeah.
At that time, I sent you two, and then we were just thinking of the third one to take outside somewhere else. Yeah, this, right? This and this we already decided. Okay,
Yeah.
but yeah, both will be very useful, and I think should be not that difficult for you. Okay.
This is not.
So those two you can register. Now, not sure finite element I will do or Dr. Wu will do. If he does, I think he will do from fluid mechanics point of view. So um, it's okay. It will still be useful.
Oh.
Yeah, I'm sure most likely he will not do from solid mechanics because he's from fluid field. Right. Yeah. You can check if this one needs citizenship.
Yeah. Finance element. Yeah. I think I registered.
This NLEF.
Yeah. Finance element is there. I think it's gonna be by when Tao.
Oh, okay, okay. No, I'm showing something else. Oh, am I not sharing my screen? I'm sharing.
Yeah, you are sharing it. Yeah, I'm just telling you I register it.
Okay, okay. No, I'm saying, did you register for this one?
No,
Yeah, I think you should.
I've not seen it on my.
Forward.
Most of these U.S. Department of Energy, they are always requiring
Yeah,
to be a citizen,
I know, but just check. Sometimes maybe they don't.
and I'm not a citizen, and there's nothing I can do about that.
Yeah, I mean, just check.
Okay, Dr. Nita, Amina Sari, is she undergraduate?
Who?
Amina Shari, or what's her name?
Sama. No,
Sama.
she's also doing master. She finished undergraduate from TSC.
Is she the one working with me on the project?
Yeah, she's very, very good.
I thought you said she's undergraduate.
No, she was undergraduate in TSU.
Now she's a graduate.
Yeah. Okay. So the bottom ones, they should be free to move in X, but fixed in Y, right? Okay, I hope you are familiar with this quarter symmetry. If not, you read it, okay?
Okay.
Just Google quarter symmetry boundary condition, you will get it, okay?
Okay.
Now, let's put horizontal edge. So we need only these. Oh, no. No, I'm not good at this. If you can look up this selection, it will be very useful.
Okay.
How to do multiple selection in Abacus using mouse.
There is no way you can do that one because it's still going to pick another member. So the best way to do is the way you are doing it right now.
No way. It should not be. I'm million% sure that there is another way.
Hi.
So how are you, Sama? Did you see my email?
Yes, I got it.
Okay.
Thank you.
Oh, hello, Samad. Hello.
Hi, Dr. Nathan. How are you?
Okay, good. How are you?
Thank you.
So there was some kind of issue with the model, so we just made it again. Okay, so we just made the hexagon lattice into statically determinate by putting one bar in between, vertical bar. Okay.
Okay.
Okay. So now, if you remember from what we discussed, this one should already work well with the affine model. There is no, you remember, right? Affine means if we, whatever strain we are applying on the boundary, each element will have the same thing, right?
Yes.
That's what we will get. Oh, by the way, thank you very much. That is absolutely correct what you said. I still haven't fixed the Excel sheet, but I'm going to fix and send it back.
Okay.
Yeah.
All
Okay. So done. So for the horizontal, we just want to fix U2 and no rotation. Then now is vertical. Oh, but I mean, one reason also, Samal, why what I was thinking is if you and Kehinde, you can work together as much as possible, that would be great. Because, I mean, you both are working on the same topic. And just the difference for you, we were going to put the torsional springs at every node, which I know we didn't figure out yet, but we will. And now later when I thought about it, I thought maybe it is possible to do in SAP instead of Abacus. It may be easier to do in SAP, but we can think of that. But anyway, I'm just saying now, overall, you two can work together, okay?
Okay.
Okay. Is she know how to use Start Pro?
That?
SAP.
A
Oh,
little
SAP.
bit, yeah.
SAP.
Okay.
SAP.
Yeah.
Okay, SAP 2000.
I know. Yeah, we
Okay.
work actually this semester a little bit. I can figure it out. Yeah.
That's fine.
Mm-hmm.
Okay. So now let's make vertical edge. Yeah, this thing also, if one of you can figure out how to select many nodes at once with the mouse. Right now, I should have figured it out, but I didn't. I'm doing one by one. Oh, See, that's what will happen. Now I need
Yeah, just click on, you click on that member back, then it's gonna deselect.
deselect. Okay.
Yeah.
But using mouse and select so many at once, that will be the best way.
Yeah, but in this case, it's still going, it's not going to select all the nodes, it's still going to select the member because the nodes and the member here, they are interconnected.
No, I mean, there should be some method to select only nodes. Let's figure out later.
Okay.
Okay. I think these are for vertical edge. Now for this, we need to allow only in Y. So these two are fixed like that. Now the corner, okay. So done now. Now loads. Yeah. I should put on each one. Let's create loading step first. Uh, Samal, you have taken finite element method, right? Any course?
No,
Mm,
not yet.
okay, not.
Next semester.
Okay, oh, so you registered for that one. Okay.
Yeah.
Also, you can register for matrix analysis of structure.
Yeah, I registered for that too.
Oh,
Yes.
okay, okay, oh, okay. You already, yeah, that's great.
Yeah.
What is the third one you took?
Special problem.
Yeah, don't take that one because let's just keep that for the end because that no, let's think because okay. Yeah, actually you're right because finite element plus matrix analysis, it is going to be quite heavy. Yeah, Kehinde, we didn't think that angle last time. So if you take finite element, matrix analysis, and micromechanics in the same semester, I think there
Going
is,
to be so hard.
yeah, there will be no way to do research.
Yeah.
Okay, then Kehinde, you also do same then. We just study on the side, the micromechanics, okay? Kehinde?
Yeah, I'm here, Dr. Nathan.
No, I'm saying just like just now Samal was saying, for you also, if you take finite element, matrix analysis, and then a micromechanics course in Vanderbilt, all three in the same semester, I think it will be overload.
Yeah, I took matrix analysis of structure, then finite element. Then you asked me to take MATLAB based program.
Yeah, that will be useful.
Or do you still want me to take this MATLAB based program for engineers?
So did he send you the syllabus?
Not yet, but I told you it's an undergraduate course.
Yeah, it is. But the thing is that because we wrote all this micromechanics code in MATLAB, so it will
Okay, let me wait. When you send me the
yeah,
syllabus, I will send it to you and see if it is okay or not.
yeah. If it is going too much into some things that we don't need, then don't take. If
I
it's
don't see
just
any MATLAB course.
okay, this one. Let's see. It is actually undergraduate course. That's why I think you did not see.
Uh-huh.
Oh, did you see, Samal? I just sent you one fellowship email,
What email?
an email for fellowship.
Fellowship.
I just forwarded this one.
Oh, U.S. Department of Energy.
Yeah,
Yeah, I got it.
okay. Uh,
It's a research opportunity.
yeah, fellowship. So fellowship, getting national labs fellowship is a very big thing. I mean, your resume will just fly up with that.
Oh, okay.
If you have national labs fellowship, then wow, then you are ready to jump.
That's nice.
Yeah, really. But of course, we need to take advantage there. Uh, there, it will be very. Okay, maybe I can just give example. Even in Vanderbilt, there is a WINS lab, material characterization lab. So that lab is open. I think it is just closed from, I think, closed from 1 a.m. to 3 a.m. That's all. So otherwise, people are working there all the time. So National Lab is also, I'm sure, like that. So we need to really do something there if we can get it first.
Mhm.
But you can keep in mind, once you get there, then the things, you have new doors opening. Okay.
I
MATLAB,
hope I can get it.
yeah, I hope so. This is the one, but it is undergraduate course. You decide, just Kehinde asked the professor for the syllabus. So let's see the syllabus. If they are teaching the things that we need, like basic MATLAB programming, then functions, uh, just writing code in vector form, all these basic things, if they are teaching, then yeah, I think it's good to take. But if they're going somewhere into computer science, and then maybe don't take. Okay. Anyway, I just sent it. Yeah. Okay. Let's come back. Loading step. Everything we just leave the default. That's fine. Now let's apply the loads. Loading step. Now let's apply at concentrated force. Yes. Just thinking, I think it should be everywhere. It will not make a difference. So we will apply only one force in unit force in y direction, and like that. Yeah, like that. So now let's see. We didn't do meshing. Huh?
Dr. Nathan,
Yes.
the direction of the load, does it matter? Because the direction is showing upward.
Yeah, it does matter because we want to get these parameters. Let's go back to your presentation.
Is it not meant to be showing downward?
I'm sorry.
Is it not meant to be showing downward instead of upward?
It's not showing downward, right?
No, it's showing upward, the direction of the load.
Yeah, it was
Right.
upward.
Right. I think it was upward. Yeah, it is upward, right?
So is it okay like this, or is it meant to be downward? That's what I'm saying.
No, it won't make any difference because see, we didn't put any conditions for buckling or anything, so it will not matter.
Oh well, in other software, it really matters if
Yeah,
you know the.
of course. If you do it in a structural software, then it will by default, it's considering all the buckling modes. So it will be totally different. But like
Yeah.
I said before, we are just doing everything is linear elastic up to
Yeah.
infinity in compression and tension. Yes.
Yeah.
Yes. Okay. Uh, no, mesh we didn't do. Let's do seed 0. That's too much. Yeah, that's what we want. See, we want one node at each joint. So then it will be just exactly comparable to our micromechanics. Okay. No mesh controls. Okay, beam element, and say okay. No mesh part. Okay. Did we do section assignment? Yes. I think should be ready to run now. Okay. Okay, beam orientation. Okay, looks okay. Okay. This is to do the finite element. Yeah, this should be fine. Okay. Just a second. Okay. Sorry. Now let's okay. Okay, completed. Uh, okay. Oh, something went wrong there.
Mm.
Okay, let's see something not symmetric. Something went wrong. Okay. Okay, let's go back, see the boundary condition. Yeah, that's not okay. Okay, let's just fix one thing. Let's save as extra vertical member. Now let's save another modified force. Okay, let's do that. In this one, let's edit the load. Oops. let's put only at these nodes. I think that could be the problem. Let's see once more. Yeah. Well,
Isn't that because the other side is not pinned?
which side? Which side?
The right side?
We don't need to pin it because it is quarter symmetry.
Mhm.
Let me see. We should not need to pin it. Should be fine. Yeah, we cannot pin it because we are trying to get the Poisson's ratio. Let's compare undeformed. Yeah, you can clearly see the Poisson's effect, right? You can see it is wide. This one is wider, right? And
Right.
after pulling, it became quite a bit more narrow, right?
Right.
Yeah, so we want that effect there. Something is off there. It could be that should not need to mesh more. I think I understood what's happening. Okay, let's do, I think, okay, I think I got. Let's go back to boundary condition. Let's do one thing. Remove this load. Now we load. I'm going to apply there. Here. There. That's okay. Yeah, that should be okay, I think. But the point you said why we are not pinning there, but we can't because it's moving up and it is moving this way as well. So yeah, we can pin. Okay. So we want 1 and 0. Should be okay now. Should be okay now. Let's see. Whoa. Okay.
So, Dr. Nita, I think,
uh-huh.
is it because, I think the reason is should be because of the effect of the load and the direction at which you pin it. Because if
Yeah.
you pin it here, if we apply the pin here, what we are seeing in this direction is going to transfer to this direction.
Oh, wait. I cannot see what you're showing. Oh, maybe I need to stop share. Okay, now you say. I'm sorry.
No, what I'm saying is, the displacement, the behavior of the member, the beam on one side is different from the behavior of the beam on the left side, on the right side, on the left side. They both different. So I'm saying the effect could be because of where you put the pin.
Yeah, that's true. So let me try.
If we have put the pin on the right hand side, what we are seeing on the right hand side will shift to the left.
Yeah, but that's not what we want. We don't want these distortions. Okay. We don't want these element distortions. So I think most likely, let's go back here. It's at the corners. It's only at the corners. So let's give one more thing for stability.
Can we remove the pin on the left side and see how is it going to look? Is it possible?
So
we should just leave the joint. The pin on the bottom. We should remove both. The one we have on the left.
Or you can change the place of the loads. The points that you put the loads.
Put in the alternate one. Okay, let me try that. I was worried that might not give the right picture. Let me try just one thing. Okay, let me try just one thing, and then I will try what both of you said. Let me just try one thing. Okay, now
no, I was saying we can only delete the vertical, then we leave the horizontal.
I'm trying to see if I put the whole thing as suppressed, because this is the entire thing is the boundary, not just these points. So I was going to let me just try once. What I'm saying is, okay, let me just show you now. Can you still hear me?
Yes, I can hear you.
Okay, my computer is stuck. Okay. Let's do horizontal range. Okay, now what I'm saying is this whole thing is the boundary. So let's just do the whole thing. I think that could be the issue. It's very slow suddenly, the remote connection. Um, so all those done. Now this should be free in one, but fixed in two. Ah, okay. We don't need to constrain the rotation. That's another thing. Okay. Yeah, that's the other thing. We are putting pin. Yeah, that's the thing. Okay. I think if we fix that, even the previous one should be okay. But anyway, let's do once. Now let's do vertical edge. Oh, no. You said just click again, Kehinde. What should I do?
Yes, you can just click on that member again. Does it work?
It's not working.
Yeah, it work. I've done it before. It work.
Okay, maybe I was doing it wrong. Okay. I don't- Yeah, I think the rotation, I cannot fix, if I put rotation constraint, it's not pin joint anymore. I think that was the mistake. But anyway, let's do this, then we go back and we do the other one. Okay, this should work, I think. Okay, okay. Then this should also.
What about this? Is it? Do we need to? Okay, no, don't worry.
Done. Now this one is fixed in X. Okay. Now, okay. Now we apply the load. Yeah. Okay, let's see now. Not bad, not bad. Just some small thing there.
Yeah, but
Yeah, just some small distortion at this corner. Yeah, I think just leaving that free will be okay. Okay, let me go fix that one thing. Just this one, I don't think I should put. Okay. The this one. Okay. U2 is fixed. Okay. Okay. Now should be. Still some distortion there, but it's very minimal. I think it's okay, just not that bad. There's a bit, but not that bad. Let's go and check the other one without the rotations. Let's just save this one. Then go back and open. Oh, I didn't realize we changed this. Let's just edit the. You restrict that is not pin joint. So that was a big issue. No, there's still some distortion. But it's gone at the top. Okay, I think you both can do one thing. Now we have this thing. We just need to adjust this a bit. Let's just calculate from the one that looked kind of okay. I think that was this one. Let's just calculate Young's modulus and Poisson's ratio from here so that you can see how to do that. And then we can go fix it, make some small adjustments. Okay.
Okay.
Yeah, just leave that small thing for now. So now this looks actually everything went to yeah. Let's check what should be the Poisson's ratio for square lattice. One, right? I mean zero, right? Let's make sure square lattice. Yeah, she wrote the wrong things in some places, but it's yeah. This should be zero. No Poisson's ratio. Just a second. Okay. So on okay. Okay. So how to get elastic modulus and those things now? Now, what you want to do is go to history output. Okay. So we want to history output results. We want to put in a new one. Continue. So, okay. So first we want to create some sets. How to create sets? So what we want to do? So Poisson's ratio. What we need? We need just 1 second. I'm trying to tell this first. Don't know if it's even I have permission. Just a second. So many. Okay. Just one moment. I need to. Okay. Just a second. Sorry. Yeah, sorry. Just one moment. I need to. Uh, sorry. Yeah, sometimes it's just not good. Yeah, really not good. I don't know what to say. Like one of the students,
Okay.
the question is about the concrete compression test. Or no, in general, we did some concrete testing. We did compression test, cylinder testing, then modulus of rupture cylinder. How you used finite element analysis there. The student is writing about pig's head and pig brain. I think they just type the words in Google and put the first thing that appears.
Oh, oh my God.
That's really, really, really not good.
Yes. I just want to pass it, not learning anything.
I mean, oh, I cannot even pass if she writes like that, right?
Right.
Like we never brought any pig into the lab. Okay. Yeah, so we need to make this kind of history output. So for that, first we need to go make a set. So we need all the information about the nodes on top because we need to know the vertical displacement. So let's make a node. Let's call this vertical nodes. Continue. So we need all these, this. We will take average of everything. Okay. Then for these nodes on the edge, we need to know how much it went in the x direction to get the Poisson's ratio. So let's define that one. Okay. Now these are vertical nodes. And for, okay. So now we go to history output, then loading step, continue. Now, not whole model, we need a set. We need, I thought we called that horizontal nodes. Hmm. Oh, oh, I myself open names. Okay. This is set to. This is this. Oh, okay. Um, okay, so we called it horizontal edge, vertical edge. So what we need right now is we will make a history output and history output 2. We continue, not full model. Okay, yes. Set take horizontal edge. So for the horizontal edge, we need U2, right? Only this. And we need the forces. This. Okay. So we say, okay, then we need another one. This is for the vertical edge. We need displacements. One. That's all. Okay. So now we have two history output requests. So when you run the job now, oh, you both are there, right? I cannot see.
Yes.
Okay. Okay. Now, when you go to result, uh, yeah, go to create XY data, ODB history output, then yes. So you see here, horizontal edge, we need all the vertical displacements. So select everything up to there and do save as. So as is, okay. So 33 XY data have been created. So now if you go to your folder, I think by default it puts in temp. So 12.1 just now, yeah, here it put 12.1 this. Okay, just a second. Not sure where it's putting the data. Yeah, see temp. Let's change that to make a folder called hexagon vertical verse output. Pick this. report. Now all these data apply. So for horizontal edge, apply. Appended to file abacus.rpt. So what we want now, you go there. Okay, so there it is. Okay. So if you just do with Notepad, now you can see everything. All the CF2 is there. Okay. So what you do now, you open this with Excel. So go to Excel here. And open. Here, here. And by the way, just reminder, always work with your network drive. Samal, can you access your network drive now?
Network drive?
Z drive.
0, yeah.
Yeah, okay, that's great. So okay, so now you have okay, so these are all forces. Okay, so the force was 1. Okay, that's fine. Now go back to abacus. These are forces. Okay. Now in another file, yeah, we want the displacements. U1 for vertical edge and also yes, U2 for horizontal edge. Okay. So let's do. Okay, and when you do that, make sure you save as Excel workbook and save this as force data. You are done with that. Now what you do is delete this abacus RPT. Okay, now go back to abacus. Now we want to output all the U2 data. So shift this, save as is. Okay. So now go to report XY. No, not this. We want U2, yes. U2, all of them. Apply. Okay, so now again there is a file called abacus rpt there. Open and go there. Open, browse, abacus, limited, space. Okay, so now we have all the displacements, right? So just take average of all of these. So this is the horizontal, this is vertical displacement of the horizontal edge. So take average of all these. Don't count that. First, all the displacements. Take the average. Okay, that's fine. Now go back there. Now what you want to put a dump is, so now you want to go back here, you want U1 at the vertical edge, U1 save as is. Okay, now report. Okay, go and delete the, okay, first save this one, save as Excel, save this as not because uh, horizontal edge 2. So close this. Now go delete that abacus file. Now go back here. Report. Now we want the horizontal edge displacement. All of those. That's correct. Apply. Append. Okay. So now go back. Open there. Browse. Lucas. Then delimited. Next. Space. Next. Fine. Okay. Again, I did the same thing. We want the U1 for the vertical edge. So let me try that again. Let me delete this. You go see what I selected. Oh, I selected U2. That's not right. I want U1 at the vertical edge now. Okay, apply. Okay. So now let's go open. Focus. Then delimited. Okay, so all are negative as we expect, right? So now take the average of these. So negative 6.7 times 10 power negative 7. So save this as your vertical edge U1, right? Okay. So this average is this much. So now check the other one. Horizontal edge U2. What was this average? 1 point. Let's just give some decimal. Okay, 1.8. And the other one. So can we do minus of lateral displacement by longitudinal displacement? What is, let's copy that value here. Special values. Okay. Now our Poisson's ratio is negative of lateral displacement by longitudinal displacement. Okay, so 0.37. This is our Poisson's ratio. Okay, is it clear?
Yeah.
Okay, now for elastic modulus. Now force is 1, right?
Yes.
Now what is our vertical displacement? This much, right? U2. And force is 1. So 1 Newton 1 Newton. Now we need to get the approximate area for that. Okay. So our thickness, you need to take a certain thickness and get the area over which the force is applied. Okay. And then you will get the stress. So basically we are converting the force to a stress and the displacement to a strain. Then that stress over strain will give us the effective elastic modulus. Is it clear?
Yes.
Okay, okay, great. So if you can get both of, oh, we already got for this one. Okay. So, okay, now the next thing, okay, now at least we have this saved video. So next time, Kehinde, Samal, both of you, you know how to do this kind of thing. So now we need to check these values against the micromechanics model, okay?
Mhm.
So I need to explain how to use that to both of you. By the way, Kehinde is not saying anything. He is still there, right? Okay, you are there. Okay, I heard you laugh.
Just listening.
Okay, okay. So everything clear, Kehinde? You are very silent.
Yeah.
So how we can find the area?
Area, okay. So
Do we know the thickness?
yes, the thickness we gave is 0.5
That
millimeter.
should be, is it going to be pi d square over 4?
No, no, it's just d, right? Kehinde, how can thickness be d square?
You say what?
Thickness, thickness.
Oh, she was talking about the area.
Yeah, yeah. Okay,
Yeah,
let me
I
draw.
just asked about the thickness too.
No,
Oh,
she
so
was just asking.
I'm like, if we know the area, we can use pi d square over 4. If we know the diameter, we are looking for area. The circle.
Hold on, hold on. Not so, no need to do all that. So if you look at it in 3D, it is like that, right? So this thing has some thickness. This is nothing but the diameter, right?
Right.
So this d is 0.5 millimeter. And the length is simply, you can go to abacus. You can go and
0.01. I mean, once.
yeah, but
One.
we need to consider from here to here. So from this end all the way up to this end. So we can do that in abacus. And, go there. Then you can go measure the distance. 0.33. So this is 0.33 meters. So for our sheet, this is 0.33 meter, and this is the thickness, which is 0.5 mm, right? So our area of cross section is this, right?
So 0.33 multiplied by
That,
0.005.
yes. So that's our area of cross section. What is our force? Our force is we applied 1 Newton everywhere. So total how many? Let's say, I know it is a kind of not good way to do it, but that's what I'm doing. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16, 17, 18, 19, 20, 21, 22, 23, 39. So Okay, the force we applied is 39 Newton. So we know our area. So now we got the stress, right?
Mhm.
Now, what is our uh, vertical dimension? Go back to this. So from here to here, 0.2 meter. So our length is 0.2 meter, and our change in length is, we need to go there. Our change in length is the U1. So, oh, sorry. Yeah, this one, 1.8 times 10 to the negative 6. Meter. So our strain is delta L over L. So we got our strain, we have our stress. So elastic modulus, effective elastic modulus is stress over strain, right? So now we got effective elastic modulus and Poisson's ratio. So those are the plane strain values E11 and nu12. So we got these two. Okay. So these two are the values what you saw in when we looked at the plane strain. Yeah. So E1 and nu12, we got these two. So we need to compare these two with the micromechanics calculation. So that will tell us how good is our micromechanics.
Mhm.
Okay, so maybe for today, let's stop here. Now, all this thing must be downloaded to my hard drive. I will upload it to YouTube right now. So maybe the next step, Kahinde, what Samal is trying to do is to, at each joint, apply some rotational spring so that we can exactly specify the rotational stiffness at every joint, okay? That's what he's trying to do. But for you, I think even for diamond, you needed to do this thing, right? That was also not working, right? The diamond with extra members. You did diamond as well, but it also had some problem, right?
Yeah.
So now that we went through the whole thing for this, can you go back and fix the diamond?
Yeah, sure.
Okay. So Kehinde, you do that, and for someone you can continue to check you can check the abacus manual, you can check other literature just to see how we can apply at the node. We want to apply torsional spring, and alternative is, I just think it may be very easy to do in SAP.
Yep.
Yeah, SAP 2000. Uh, I I just think you can try both, whichever one is easier, okay? Because in SAP there is a direct method. You can go to the joint, you can put a spring there.
Okay.
So you could try both. Okay, let's just stop over there for now. And one thing you can do in the meantime is both of you have read that paper. So you both can discuss that paper for a bit, and then we can meet again, I think tomorrow or day after. Okay.
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 So
Tomorrow at
uh,
what time?
not sure. I will.
You will let us know.
Yeah.
Okay.
Okay. Okay. Okay. So I will go now. Yeah. Okay. Thank you.
Yeah, thank you. Yeah. Thank you.
Thank you. Yeah, I
Thank
will
you.
upload.
And that's one thing. Did you record? Yeah, you record this.
Yes, yes. So
Okay. Can you send this to
yeah,
us too?
yeah, I will need to upload the recording to YouTube,
Mhm.
and then it will all be there. Yeah.
Okay. Thank you.
Thank you.
Have a nice day.
You too.